In this lecture, we're going to look at section 1.8 out of the book, Introduction to Linear Transformations. So first off, a definition. A function, or a transformation, from one set to another is a rule that assigns every element in the first set to an element in the second set. When we talk about functions in general, we aren't talking about matrices. We're going to talk about matrices in a minute. But a function in general is just a rule that says for everything in your first set, we associate it with something in the second set. The first set is called the domain, and the set that things are turning into is called the codomain. Another definition, the range of a function is the set of all possible values, all of the things that you might end up with. Now, the range and the codomain are two different things. They may be the same depending on what your function is, but they might not be. We're going to talk about that in a minute. So, as an example, here is a function. A function is a relationship between two sets. So our first set is the numbers 1 through 5. Our second set are the colors red, green, blue. Now our function is defined, remember a function is just something that associates everything in the first set with something in the second set. So here's a rule. F of n, so f of any element in that first set, is red if n is odd, blue if n is even. Okay? So note that the function has a rule for every member of A. That's a function has to have that. It has to have something for every member of A. But also note that not every element of B is obtained. We have a way of getting red, we have a way of getting blue, but there's no way of getting green. So this is an example of those terms I was talking about. The domain of F, those are the starting points. So that's my original set. The codomain is the set that I'm going into. The range are all of the possible things in that set I'm going into that I can actually achieve. Not everything is achievable sometimes. So that's the idea of the domain, the codomain, and the range. And we are going to be discussing these terms in terms of matrices and linear transformations. So we just talked about functions in general, from one set to another. We can talk about functions in terms of sets of vectors, and this is what we're more interested in. We're interested in taking a vector and turning it into another vector and looking at the rules around that. So for example, if we have a function from R2 to R2, and here is a definition of a function. So it takes every element of R2 and creates a new vector out of it. Find this. Well, f of xy is that rule. So that is equal to 3 times the top element, 3 times 2, plus the second element, minus 1. And the second thing in the image is the first element, minus 2 times negative 1. So that is 6 minus 1. And the bottom is 2 plus 2. So that is 5, 4. That is a function. I have taken the vector 2, negative 1, and I've transformed it into the vector 5, 4. Another example, that one was going from R2 to R2. We don't have to have the same size vectors. This is a case where you have a size 5 vector going into a size 3 vector. And again, we just have a fairly simple rule for it. So we can find the transformation, or it's called the image of that vector by just filling in our rule. So it's 3 times 1 plus 2. The second one is minus 3 plus the fourth element plus 4. And then we have 2 minus the third element, so minus 3, plus 2 times the fifth element, minus 5. And that equals 3 plus 2, minus 3 plus 4, and 2 plus 3 minus 10, which equals 5, 1, and negative 5. So there's my transformation. I've transformed a 5-dimensional vector into a 3-dimensional vector using the rule when I define the function. So that's the general idea of function, the general idea of vector function. Now we're going to talk about a matrix transformation or a matrix function. Generally, when you're dealing with linear stuff, you talk about a transformation, just kind of the terminology that's generally used. Sometimes you'll see it termed matrix transformation. Sometimes you'll see it termed matrix function or linear function, but transformation is kind of the more common term when you're dealing with matrices and linear items. Okay, so A is an m by n matrix, and X is any vector in Rn. We're going to define the function or the transformation. So this is the function, t of x, the transformation of our vector in Rn, is simply equal to our matrix times that vector. So on the previous slide, we saw that the transformation was defined as, and then I gave you a 3-dimensional vector that said x1 minus x2, x3 plus x4, or something like that, whatever it was. This time, I'm going to define my function as multiply some matrix and some defined matrix by whatever vector you give me. That is called a matrix transformation. This takes any vector in Rn and transforms it into a vector in Rm. And you'll sometimes see it designated that way as well. X, that need little arrow to AX. So this is another transformation. So as an example, here is a transformation from R3 to R2. And the transformation, the definition of it is this matrix times your original, times the vector that you're starting with. So for example, t of 1 to negative 1 is equal to 2, 3, 2, negative 1, negative 3, 2, times 1, 2, negative 1. And we saw how to do matrix vector multiplication. It's equal to 1 times the first column plus 2 times the second column minus 1 times the third column, which gives me 2 plus 4 plus 3, and 3 minus 2 minus 2, which is 9, negative 1. So it's taken a 3-dimensional vector to a 2-dimensional vector. And note that if you are doing a matrix transformation that goes from R3 to R2, you need to use a 2 by 3 matrix. In general, if you're going from Rn to Rm, you have to have an m by n matrix. There's another example of matrix transformation, the kind of thing that you could be asked. Is 1, 2, 3 in the range of this matrix transformation. In other words, remember the difference between codomain and domain, and range. So codomain just means R3. So that's in the codomain. It is a three-dimensional vector. It is in the codomain. That is not a guarantee that it's going to be in the range. To be in the range, I have to be able to find something that I can put in here to start with that turns into that vector. And you can't always do that. So we're going to see, is the matrix 1, 2, 3 in the range of this transformation? So in other words, can I find a vector x1, x2 where t of x1, x2 is equal to 1, 2, 3. Well, what's t of x1, x2? That is equal to this vector, 2, 3, 2, 2, minus 1, 0, times x1, x2. And what's that equal to? That is equal to 2x1 plus 2x2, 3x1 minus x2, 2x1. That is equal to 1, 2, 3. Well, look at what we have here. We have a system of linear equations. Now, with this system of linear equations that we've just seen, we know how to solve this. We can put it into an augmented matrix. So what is our matrix? Our augmented matrix would be 2, 3, 2, 2, negative 1, 0, 1, 2, 3. That's our augmented matrix that we got from that system of linear equations. So let's start to row reduce this. I'm going to note that if I take row 1 and exchange with row 3, because my row 3 looks kind of what I want to get my row 1 to look like eventually. That's a good first step. Now I can row reduce this a little bit more. I can take 3 times row 1 minus 2 times row 2 is the new row 2. So I get 2, 0, 3. I am going to get 0, 2, 9 minus 4 is 5, 2, 2, and 1. Now I am going to do row 1 minus row 3 is the new row 3, 2, 0, 3, 0, 2, 5, 0, minus 2, and 2. I am going to do row 3 interchange with row 2, 2, 0, 3. Now there are plenty of ways to do this. This is just one way of getting through the row reduction. Now I'm going to take row 2 plus row 3 is the new row 3, 2, 0, 3, 0, negative 2, 2, and 0, 0, 7. Note what we have now. This final row, that is giving us a leading entry in the augmented column. That means there is no solution. When there is a leading entry in the augmented column, there is no solution. That means the vector I started with is not in the range of t. I can't get it. It was in my codomain, but it is not in my domain, or in my range, because I can't find anything. There is no way to find something to start with that will turn into that vector. So this is an example of a function where my codomain is different from my range. Okay, next concept is a linear transformation. So far we've seen a general transformation or a general function. We have seen a matrix transformation where the transformation is take a matrix and multiply it by a number or by a vector. Now, we're going to forget about matrix transformations for a second, and we're going to say, in general, any kind of transformation is called linear if it has these two properties. First off, adding two vectors together and then applying the transformation is equal to applying the transformation of the first vector, then adding it to the transformation of the second vector. In other words, it doesn't matter if you add your vectors first or if you add them afterwards. You get the same thing. The second one is that when you're multiplying by a scalar, it doesn't matter if you multiply your vector first and then do your transformation, or if you transform first and then multiply by your scalar. When these two things happen, no matter what vectors you put in, if it always happens this way, it's called a linear transformation. So here's an example. We have this transformation, and we're asking, is it a linear transformation? To show it's a linear transformation, show whether or not it's a linear transformation, we have to show that those two properties hold. So the first property said that t of u plus v is equal to t of u plus t of v, no matter what vectors you take. So I'm going to say, okay, my transformation is from R3 into R2, so I have to start with two things in R3. So I'm going to let u equal x1, x2, x3. Actually, I used the x up above, so I'm going to use u1, u2, u3. I'm going to let v equal v1, v2, v3. Now I have to show that both sides of this equation are equal, no matter what I put in there for u's and v's. So t of u plus v plus v1, v2, v3, that's equal to, well, we have to add things first because they're in the brackets. u1 plus v1, u2 plus v2, u3 plus v3. And now we have t, we're saying transform this vector. So this is equal to our matrix 2, 3, 2, -1, -3, 2 times u1 plus v1, u2 plus v2, u3 plus v3. And now we have to multiply. So this is equal to u1 plus v1 times 2, 3 plus u2 plus v2 times 2, -1 plus u3 plus v3 times -3, 2. And when all is said and done, what do you get? You get 2 u1 plus 2 v1, plus 3 v1. Yep, so sorry, plus 2 v2 v1 plus 2 u2 plus 2 v2 minus 3 u3 minus 3 v3 for the top row. And the bottom row, we get 3u1 plus 3v1 minus u2 minus v2 plus 2u3 plus 2v3. So that's what we get on the left-hand side. What about on the right-hand side? On the right-hand side, we are trying to calculate t of u plus t of v. What's that equal to? T of u1, u2, u3 plus t of v1, v2, v3. Okay, so this time we're going to transform first and then add. So what is this? This is 2, 3, 2 minus 1 minus 3, 2 times our first vector plus 2, 3, 2 minus 1 minus 3, 2 times our second vector. Well, now we can do each of them individually. We get u1 times 2, 3 plus u2 times 2 minus 1 plus u3 times negative 3, 2 plus, and now we're on to our second group, v1 times 2, 3 plus v2 times 2 minus 1 plus v3 times negative 3, 2. Add them all up, and I'm going to rearrange them just a little bit. I get 2u1 plus 2v1 plus 2u2 plus 2v2 minus 3u3 minus 3v3. And on the bottom, 3u1 plus 3v1 minus u2 minus v2 plus 2u3 plus 2v2. This is the same exact thing. So this shows that t of u plus v is equal to t of u plus t of v. So that means our first condition holds. What about our second condition? We have to show that t of cu is equal to c of tu. In other words, it doesn't matter which one you do first. I leave this as an exercise. Do the same exact thing. Figure out the left side first, then figure out the right side. Make sure that they equal each other. Okay? That is what you have to do to say something is linear. In this case, it is. This is a linear transformation because no matter what you put in there for u and v, the equalities hold. For any linear transformation, you are going to get some other properties. You are going to get that t of 0 equals 0. Anytime you transform any linear transformation, if you transform the 0 vector, you will get the 0 vector. And there's a quick proof for that. Let's say u and v, let's say that u is any vector. If something is linear, that means t of u minus u is equal to t of u minus t of u. Because linear means it does. Remember, subtraction is just an addition. Because it's linear, it says we can add first or we can transform first. So what does that mean? Well, t of u minus u is 0. So t of 0 is equal to t of u minus t of u. That's something minus itself. That's 0. So as soon as you know something is linear, it means that the transformation of 0 has to be 0. Now, if you think about what you normally call a linear function from x to y on the plane, you often think about a linear function being a straight line. Well, a linear function being a straight line is not a linear transformation. A linear transformation would have to go through 0, 0. A straight line that doesn't go through zero is a function, but it is not a linear transformation. Okay? Make sure you understand that difference. Why isn't it a linear transformation? Because it would violate this rule. Okay, second thing. T of negative u equals negative t of u. Well, that's just by multiplying things by -1. Multiply your vector by -1, multiply your vector after your transformation by -1, you get exactly that. That, the third one, is just the same as addition, but you're subtracting. I kind of jumped the gun up here and used that, but it's the idea that subtraction is the same as addition of something times -1. And finally, now this should start to look familiar. When we talked about what a linear function was, well, it was essentially something that looked like this. It was a number times a vector plus a number times a vector. Well, here what we're saying is that when you can do your number times your vector plus the number times your vector and then do your transformation on it. Or you can do the transformation to each of the vectors in turn and multiply by the corresponding numbers. You're going to get the same thing. The rule says that it works for two of them. If you think about it and work on it a little bit, you're going to see that it works for however many of them you want. Any finite number of vectors that are combined linearly, you can transform them after, or you can transform them before. And you can also say that this is equal to t of a1u1 plus everything up to t of an un, because the rule says you can take those numbers in and out. Okay. So a linear transformation gives you this flexibility to transform before you do operations or after you do operations. Okay, that's section 1.8, the basic ideas of linear transformations. Section 1.9, we are going to delve into them a little bit more.